Hi, my name is Spencer Klein. I'd like to tell you about some of the interesting neutrino interaction physics that we can study with IceCube. I'll start out by talking about the science we can do with neutrino interactions, then talk about cross-section and inelasticity measurements, and then draw some conclusions. In the standard model, neutrinos interact via charge current interactions, shown on the left via W exchange, and via neutral current interactions, as shown on the right, via Z0 exchange. These are sensitive to the parton, mostly quark distributions in the target. The higher the energy neutrino, the lower Bjorken X, or momentum fractions of the partons that you probe. Here, the cross-section and inelasticity measurements are complementary. Cross-sections probe X over a wide range, whereas with inelasticity, a given neutrino energy and inelasticity correspond to a particular Bjorken X. So in some ways that's more selective, although the statistics are a bit lower. And the other interesting thing is this is also sensitive to a wide variety of beyond standard model physics, which would add new neutrino interactions. These include the possibilities of extraspatial dimensions, leptoquarks, spectrons, and much more. And already some of the neutrino cross-section tests from IceCube are competitive with LHC results. This plot here from the Snowmass white paper shows the energy landscape for neutrinos. On the left, we have fixed target experiments at Fermilab and CERN, where the Fermilab neutrino beams reach 500 GeV. Unfortunately, those are no longer available. To go higher, it's possible to use neutrinos from the Large Hadron Collider, where energies up to about 7 TeV are accessible. On the other hand, IceCube goes up to here, can reach neutrino energies of about 10 PeV, or 1,000 times higher. And the coming next generation radio detection experiments, including Gen 2, should observe GZK neutrinos with energies in the 10 to the 19th or 10 to the 20th electron volt range, another 1,000 times higher. The disadvantage here is that these are relatively low rate experiments, and you need about 10 to 100 events for a measurement. On the other hand, when you get that, you're probing energies above the Large Hadron Collider. Cross-section measurements work by measuring neutrino absorption in the Earth by looking at upward-going neutrinos that go through the Earth at different chords. And they're usually measured as a multiple R of the standard model charge current and neutral current cross-sections. This has been studied with tracks, primarily muon neutrinos, and showers, which are primarily electron neutrinos and some all-flavor neutral current interactions. As you can see from this plot, the cross-section rises with the neutrino energy. You need a minimum neutrino energy of 1 to 10 TeV to get enough absorption for a good measurement. On the other hand, at the high energy end, the maximum energy is statistics limited and is currently of order 10 to the 16th EV for IceCube. Inelasticity measurements are somewhat complementary. They use starting track events that are actually observed in the detector. If you measure the energy of the hadronic cascade when they are initiated, shows the energy transferred to the target, and the muon energy, you can then calculate the inelasticity as the ratio of the cascade energy to the total energy. These distributions are sensitive to the parton densities and, as I mentioned, BSM physics. The energy range here is from order currently about 100 GeV up to the statistics limit, again, about 10 PeV. And potentially much higher with radio, although there are some details to be worked out. This plot here shows the IceCube inelasticity measurements as a function of energy, along with predictions for neutrinos and antineutrinos. So my conclusions: large neutrino telescopes like IceCube KM3Net and IceCube Gen 2 can measure important properties of neutrino interactions. Their neutrino cross-sections and inelasticity are sensitive to both the standard model parton distributions and to BSM physics. Already, some IceCube BSM limits are competitive with the Large Hadron Collider. Gen 2 will push this higher and will be able to explore physics at an energy scale above the LHC. Thank you.